Welcome to today's Explainer. Right now, you and I are going to embark on one of the most incredible, high-stakes journeys happening inside your body at this very moment. I'm talking about the continuous, microscopic, anatomical journey we take with every single breath. We do it thousands of times a day without even thinking about it, but the biological machinery making it all possible, it is absolutely mind-blowing.
To really put the sheer power of this system into perspective, let's start with a crazy number, 22. Most of us can hold our breath for, maybe 30 to 60 seconds before panic sets in and that urge to breathe becomes totally overwhelming. But the world record for a human holding their breath underwater, an astonishing 22 minutes. There's just no way to think about that without realizing it completely redefines what the human body is capable of. It truly showcases the extreme capabilities of your lungs when they are pushed to the absolute limit.
So, that really begs a fascinating question for us to explore today. How much do you actually know about the system that's literally keeping you alive right now? How exactly does a gulp of air from the outside world navigate through this complex labyrinth of macroanatomy, all the way down to a microscopic cellular interface? Well, we are going to follow the exact path of a single breath and break the whole shebang down, step by step.
Here's our roadmap for today's journey. We'll be moving through 5 parts. First, the upper respiratory tract. Second, the lower respiratory tract. Third, the gas exchange zone. Fourth, the mechanics of breathing. And finally, recognizing pulmonary disease. Okay, Section 1, the upper respiratory tract. Let's dive right in and explore the entryway, where the outside air first makes contact with the human body. Let's track the actual structural flow of the upper respiratory tract, because it follows a very clear physical path. When you take a breath in, air is drawn first into the nasal cavity, sweeping right past the cartilaginous entrance of your nose. From there, it flows seamlessly into the pharynx, which we just commonly call the throat, and then it travels down into the upper portion of the larynx. It stops right above your vocal cords, pausing just briefly at this ultimate gateway before plunging into the deeper lower tract.
Notice how the paranasal sinuses, like those prominent frontal and sphenoid sinuses, surround the nasal cavity. Now, these aren't just empty, useless spaces. They actively work together with the pharynx to prepare the air. Together, they provide a clear airway, they enable speech and swallowing, and most importantly, they condition that harsh outside air for the delicate, microscopic journey it has ahead.
But here's a really cool behind-the-scenes fact. Your upper airway acts as an incredibly efficient instant heater. The ciliated epithelium and nasal membranes don't just filter out dust and debris, they heavily modify the air itself. Let's say you breathe in frigid winter air at 6 degrees Celsius. Your nasal cavity will drastically warm that air all the way up to 30 degrees Celsius before it travels deeper. It's basically a fully automatic climate control system, making sure the delicate tissues down below are never shocked by the cold.
Section 2, the lower respiratory tract. We're now traveling below the vocal cords and entering the branching tree of the chest.
Now, the absolute crucial point in this lower tract is understanding that it's divided into 2 distinct functional zones. First, we have the conducting airways, which includes the trachea, the main bronchi, and the first 16 generations of bronchioles. In this zone, air is simply traveling. It's essentially anatomical dead space. But, this dead space is vital. It gives the rushing air momentum, allows for further conditioning and humidification, and guides it precisely where it needs to go. Once we hit bronchioles 16 through 23 and the alveoli, we enter the respiratory airways. This is the active zone, where actual life-sustaining gas exchange finally happens.
Before we trace the air any further, just consider the gross anatomy of the adult lungs for a second. The right lung has 3 lobes, while the left has only 2, which makes crucial room for your heart. But here's a truly surprising fact. Despite their massive physical volume and absolute necessity for our survival, adult lungs are surprisingly light. They weigh only about 1,000 grams in total.
And inside those lobes is a brilliant piece of biological architecture, the tracheobronchial tree. You can see how the trachea, supported by its rigid C-shaped cartilage, splits right at the carina into the main right and left bronchi. From there, it's a constant, repetitive branching into ever smaller bronchioles. It transitions beautifully from those rigid, wide-conducting airways down into the extremely delicate, highly branched respiratory airways, essentially spreading that single breath of air across your entire chest.
Moving on to Section 3, the gas exchange zone. Let's zoom in dramatically to our ultimate microscopic destination.
To truly grasp the staggering scale of the respiratory system, you need to understand this one number, 300 million. That is the estimated number of microscopic alveoli packed inside your lungs right now.
This sheer volume creates an absolutely massive surface area. We're talking roughly equivalent to half a tennis court, all folded up neatly inside your chest, entirely dedicated to keeping your blood oxygenated.
Down at the ends of those respiratory bronchioles, you'll find these terminal alveolar sacs clustered tightly together. Notice how astonishingly thin the walls are. They form the absolute thinnest possible barrier between the single breath of air you just pulled in and your rushing bloodstream. Consisting of type 1 squamous cells and type 2 cuboidal cells, they create this perfect, highly permeable interface for oxygen and carbon dioxide to rapidly swap places.
Section 4, the mechanics of breathing. We know exactly where the air goes now, so let's shift our focus to exactly how that air gets pulled in to begin with.
It's really a beautiful relationship between your nervous system and your chest muscles. Think about the diaphragm, that powerful dome-shaped muscle right at the base of your rib cage. When it contracts, it flattens out, forcing the chest wall to expand and massively increasing your lung capacity. This creates a literal vacuum that just pulls air right in. But driving all of this is an intricate nervous network. The phrenic nerve directly commands that diaphragm, while a complex web of sympathetic and parasympathetic nerves acts kind of like a gas pedal and a brake, constantly expanding or constricting your airways to regulate the flow precisely to what your body demands.
And because of those mechanical forces, we complete a three-part relay race known as respiration. First up is pulmonary ventilation. That's the physical, mechanical inhalation and exhalation of breathing. Second is external respiration, which is that microscopic gas exchange we just talked about between the alveoli and the bloodstream. And finally, internal respiration, where the bloodstream travels outward to your body's tissues, delivering that life-giving oxygen directly to your cells so they can actually create the energy you need to survive.
Section 5. Recognizing pulmonary disease. Now, what's really interesting is how we apply this precise anatomical map to recognize actual clinical signs of disease in the real world.
First off, we've got to establish what's normal. A normal baseline respiratory rate drastically slows down as a human ages. At birth, an infant breathes incredibly fast, right between 30 to 60 breaths per minute. But by the time you reach adulthood, your lungs are so well developed and the anatomical system is so incredibly efficient that a normal resting rate drops all the way down to just 12 to 20 breaths per minute.
But when the body's physiology is stressed out, that breathing pattern shifts radically. Think about Kussmaul respiration, an increased rate and depth of regular deep breaths. This is often a critical sign of metabolic acidosis, like in diabetic ketoacidosis, where the body is literally trying to blow off excess acid. Or consider buyout respirations, which is rapid, deep breathing suddenly followed by complete, terrifying pauses, or apnea. This alarming pattern is directly linked to severe central nervous system injury. So the nature of the breath is quite literally telling us what is going wrong deep inside the body.
This is where clinicians become detectives. They can physically assess the state of the internal anatomy just by listening and tapping on the chest. If a doctor taps on the chest and hears a dull percussion sound alongside crackling breath sounds, well, they know they're likely dealing with consolidation. This means fluid or solid material is filling up those delicate alveolar airways. If instead they hear wheezing and a hyperresonant, drum-like sound, they're looking at bronchospasm, a tightening of the smooth muscle. And if the chest is shifting and breath sounds are completely reduced or absent, it strongly points to atelectasis, which is an actual physical collapse of the lung tissue itself.
Which brings us all the way back to you. After exploring everything from the instant heater in your nose, down the branching tracheobronchial tree, all the way to those 300 million alveolar sacs exchanging gas at a microscopic level, how is the intricate tree inside your chest functioning right at this very moment? Take a deep breath right now. Feel your diaphragm contract. Think about the flawless journey that single breath just took. I really hope this explainer has left you fascinated by the invisible miracles happening inside you every single second. Thanks so much for joining me, and keep on learning.